Okay, first of all, was everyone able to access the slides okay this time? Can you see the slides for today? Okay. So a couple announcements. There's no class on Monday, so Elizabeth is going to have office hours next Tuesday, so we'll announce that. Quiz 1 will be returned back next Wednesday. I think, I'm not sure homework 3s are graded yet, but they'll be returned back soon as well. But those are on CT, so hopefully you don't need those for the MR part so much. Anyways, before we get started with the lecture, are there any questions from last time? Okay, any questions about the homework? Oh, you already turned it in, so okay. All right, so today what we're going to do is we're going to continue our discussion of MRI. We're going to review a little bit what we talked about for our excitation. Then we'll start talking about transverse and longitudinal components and relaxation. We'll get into the Bloch equation, a little review of K-space, and then we'll spend the last half hopefully talking about encoding with gradients, which is basically how we start making images using MRI. So just to remind you what we talked about last time. So the magnet for there's sort of 3 coils, and one of the coils is the large magnet, and this shows a picture of the magnet at our center being lifted on a crane and put into the building. And the job of that magnet is to create this polarization, this magnetization that we're going to be working with. Okay, and the bigger the magnet, the more polarization there is, and so therefore that's why there's a trend towards bigger magnets. The second step, which we talked about, was exciting that magnetization away from its equilibrium position. And we're going to talk a little more about that today. And the basic idea is we want to get that magnetization away from the longitudinal plane into the transverse plane, where when it precesses around, it can create a time-varying magnetic field, which we can then measure. Okay. And then what we'll be talking about today is how do we use gradient coils to impose spatial patterns on the magnetization, and that's what we're going to have to use for imaging. And then we'll also talk a little bit about how the RF coil is also used to receive, which is integrating the signal, which is also part of creating the Fourier transform. So to review, last lecture we talked a little bit about magnetization starting off in the longitudinal axis, and then if we apply an RF pulse at the resonant frequency, that will slowly spiral down to the transverse plane. All right? And since that's a lot of bookkeeping to keep track of, it's much easier if we go into what's called the rotating frame of reference, where everything is going at the same rate. And so in that rotating frame of reference, if I have the main field is this way, I apply a B1 field here, that's rotating. Okay. But in the rotating frame of reference, this B1 field stays constant. Okay? Magnetization just precesses around that into the transverse plane. All right? So that's what's shown in this picture here on the upper left, over here, and then if we play this movie, we're seeing that as well. So that's basically, see the B1 field in cyan is staying constant, and the red magnetization is tipping down. All right? So that's in the rotating frame of reference, which we'll also revisit again when we talk about encoding. So we need to talk about or give you the expressions for free precession about a static field. All right. So what we're going to do is we're slowly going to build up the Bloch equation, which is the governing equation for all of MRI. And the first step is this piece here, which is the fact that the change in magnetization is related to the cross product of the magnetization and the applied B field. Okay. So this is the magnetization, and this is the B field. So I've already tipped the magnetization away from longitudinal. We're talking about the precession of this magnetization around the main B field. Okay, so that's what we're talking about now. All right. So as we talked about last time, because this has angular momentum, and because the force on this is going to be given by the dot product of the M cross B. Okay. So this is the B field, and this is the magnetization. The dot product is going to be pointing this way. So it's going to have a vector going this way, which is going to make things want to go around. All right. So if you remember from way back in high school, you looked at the cross product and you realized you were told that you can be write it as a determinant. Okay, so that's this step here. Whoops. And then you evaluate the determinant and you get this expression here. Okay, so we're not going to go through that, but that's just what the expression is. So on the left-hand side, you'd have dmx, dt, dmy, dt, dmz, dt, and this would be sort of your vector. Okay, so you have a vector on the left-hand side and it's equal to some expression on the right-hand side. So the next step is just to rewrite that as a matrix product. So what we can do is we can have a matrix on this side which is composed of mx, my, mz, and then all the b terms are in the matrix itself. All right? So before we get into the solution, we are going to use phasors a lot. Understanding phasors is sort of fundamental to understanding MRI. The nice thing is it's also fundamental to understanding Fourier transforms. And so if we talk about phasors, we can sort of combine the two together and get a better, deeper understanding of each one. So just to remind you, we will use phasor notation quite a bit. So e to the j theta is equal to cosine theta plus j sine theta. Okay, so, and the interpretation is that's just a vector on the unit circle. And theta is just this angle here that vector makes. All right? So theta of 0 is just at the origin. Theta of minus pi over 2 just goes that way. Theta of pi goes there. And theta of pi over 2 goes the other way. All right? So nothing magical. Just if you see e to the j theta, then the theta is just the angle. All right? So anytime you see e to the j something, if you can get it in the form of e to the j and see what the theta is, then you'll understand what's going on. So let's talk about that in terms of precession. So in this case here, what I've done here, so notice here I have these by, bx, by, bx terms here. Now after I've sort of tipped my magnetization, I'm assuming there's no other fields except for the B0 field. Okay? It's for the first order understanding. So I can get rid of all those other terms and just have my BZ term left. And that BZ term is the main field. So we replace BZ with B0, which is the main magnetic field. And now all we have to do is look at what does this equation of motion tell us is going to happen. All right. The first thing we can say is that we know that dm z dt is going to equal 0. Okay. So that means the z component, according to this equation, is not going to change. And so we don't have to worry about the z component. So we can just worry about the mx and the my components. All right? So this is going to be super, super useful to define a complex notation where m is equal to mx plus j my. Okay? And so therefore we can use this phasor notation to describe the magnetization, what the magnetization is doing, because it has mx and my components. All right? And if we do that, it turns out that you can write the equation of motion as dm dt equals minus j gamma b0 m. Okay, where m was that complex number. And the solution turns out to be really nice. It's m of t equals the initial magnetization times e to the minus j gamma b0 of t. Okay, and we'll write that as e to the minus j omega naught of t, where omega naught is equal to gamma B0. Okay? So remember, this is our Larmor frequency. Okay? So what we have is that we have m of t is equal to m naught times this complex exponential e to the minus j omega naught t. Okay? So if we break that down, then that's of the form e to the j theta, right? So therefore theta must equal minus omega naught times t. All right. So if that's the case, then in this picture, is the precession, if theta is equal to minus omega naught t, is the magnetization going to go clockwise or is it going to go counterclockwise? So, okay, so let's see. Let me draw it this way. So clockwise would be this way, and counterclockwise would be this way. Okay, and where this is your x and your y components. Okay, so if the theta angle is minus omega naught t, will it go clockwise or counterclockwise? Clockwise, right? Because the thetas are becoming more negative, right? So if you start off at 0, then at time equals 1, it's going to be minus omega naught, and then minus 2 omega naught, okay? So when you're doing these problems, there is a preferred direction for precession. Okay, spins don't just randomly precess wherever they want. They precess in one direction, and that's going to be very important. Okay? Just the same way when I did the bicycle wheel, depending on which way I turn the wheel, it will precess in one way or the other. So because the spins have a certain angular momentum, they will precess in a certain way. Right? Okay, any questions before we move on? All right. Okay, so the next thing we want to talk about is what happens in the rest of the MR experiment. So the first part is, this is the excitation. So we're applying an RF pulse. This is the B1 field that we're applying. So we apply this B1 field here to our sample, okay? And that takes the magnetization and flips it into the transverse plane. Okay, and so now we said that once we're in that thing, then the magnetization just precesses, right? It precesses at a frequency of omega naught, okay? And it does it clockwise. Now the next thing is nothing lasts forever, so it's going to slowly decay away. It's not going to do this forever, because where does it want to go back to? It wants to go back to here, okay? So now we will need to talk a few minutes about relaxation. And what we're going to do that today, I'm just going to tell you what relaxation looks like. Whoops. I thought I could fix that. And then in a later lecture, we'll get into the actual mechanisms of relaxation. So for today, just sort of accept that relaxation occurs. In a later lecture, we'll tell you sort of more of the biological and physical principles of why relaxation happens. All right? The bottom line is there is something called free induction decay, which means if you tip some magnetization and it precesses, it will die away slowly. So this is another picture of it. So it's basically oscillating back and forth. And that's the precession. And this signal here is essentially we stand here with a little coil of wire, which is our receiver coil. And as that magnetization comes around each time, this is creating an oscillating electric field in this coil, okay? Because the magnetization is going like this, right? So that's what gives rise to all these oscillations here, right? So the magnetization is going like that. And as it's sort of spiraling in, so you notice it starts off here and it sort of spirals in until it goes away. All right, so what we want to do is talk about that phenomenon today. So there are two types of relaxation. There is longitudinal relaxation and transverse relaxation. Okay, so longitudinal relaxation is the relaxation of the M sub Z component, and transverse magnetization is the relaxation of the MXY component in the XY plane. All right. Now they're related, but they actually have different fundamental mechanisms. So that's why we actually have to have two time constants. Okay. So we'll use T1 to represent the time constant for longitudinal magnetization, and we'll use T2 to represent the time constant for transverse relaxation. So this is what longitudinal magnetization looks like. So if I have a 90-degree pulse, right, if this is my magnetization here and I flip it into the transverse plane, it's going to precess around, right? So I have a 90-degree flip angle. At time equals 0, what's M sub Z equal? It's 0, right? Because there's nothing pointing up. I've tipped all the magnetization from here to here. So the idea is it wants to slowly return to equilibrium, okay? And it's going to return to equilibrium with an exponential recovery with a time constant of T1. Okay, so this is exactly the same thing you get like if you charge up a capacitor or something. There's just going to be this charging up of the magnetization again. All right. So that's what the magnetization looks like. This is the governing equation, which will give you a problem on this week's homework. Also, because there's no class on Monday, this week's homework will be a little shorter. Okay. And so you'll have a chance to work with that equation on this week's homework. So why are we talking about relaxation? Well, it's because different tissues relax at different rates, and that's what's going to give rise to how we can make different image contrasts. Okay, so we'll talk about it in a little later lecture today. Just telling you that different tissues have different T1s. Okay. Transverse relaxation is essentially this dying away of the transverse magnetization. Okay, and it follows this very simple first order differential equation, which is just going to be an exponential decay. Okay. And so this is what that looks like. It's basically after I tip the magnetization, so all the magnetization is pointing here. Okay. But what happens is if we imagine a bunch of spins in some volume, they slowly get out of phase. Okay. And so after time, the spins aren't all pointing in the same direction. Okay. And over time, they get even more out of phase. Okay. So what's happening to the vector sum of those spins over time? It's becoming smaller. And the limit is going to go to 0. Once the spins are randomly dephased, you're going to lose all your signal. Okay? So we're going to get into the details of that later, but for now, just realize that there's this random dephasing. So what it looks like is there's still this oscillation. Whoops. There's this oscillation that's going on. So that oscillation is the precession, right? On top of that oscillation, there's that decay. So the envelope of the magnetization is decaying away with a T2 time constant. All right? And once again, T2 is really important because different tissues have different T2s, and also the T2 can change with disease. Okay, so both T1 and T2 change with age, change with disease, change with different factors. And so that's why we want to be able to measure them. All right. You notice here the T2s are actually very, very short, on the order of 100 milliseconds or so, or less. That's what really determines the time constants of our MR experiments, which means we only have 100 milliseconds to gather our data before it's gone, right? We tip our magnetization, it processes, and then in 100 milliseconds it's mostly gone. So that's why there's this real focus on speed. We're always trying to go as fast as possible because we only have a limited amount of time to collect the data. Okay, so putting together, this is what the Bloch equation looks like. We talked about this part already. This is the precession. That's just the magnetization going around the B0 field. Okay. There's a transverse relaxation, which is the decay in the MXY plane. And there's a longitudinal relaxation, which is the growth of the longitudinal MZ component back to its equilibrium value. So those three things are going on at the same time. So we can write that equation in matrix form like that. And then what we can do is we can look at the different components. So the Z component solution, this is its governing differential equation, and this is the equation, the solution for it. So that you'll use this formula in your homeworks. And the idea is, it's basically, the physical picture is wherever you start, you're always going to go back to M0. Okay? So saturation recovery is I start off at 0, and I go back to M0. Okay? Inversion recovery is I start off at minus M0, but I still return to M0. Okay? And the interesting thing about this is notice that it goes through 0 at some point in time. And that we'll see later that turns out to be super useful because it means that we can actually null out different tissues. Like let's say there's a lot of fat in my image and I say, well, I don't really want to see the fat. I want to see everything except for the fat. It means I can tip the magnetization, and then if I acquired exactly the right time, at that point where fat has 0 signal and I acquire my image, then I basically erase the fat. All right? Question?
And essentially to reverse that component, you just have to apply stronger field in B1.
What do you mean? Oh, you mean to get to the minus M0?
Yeah.
Yeah, so basically, right. So you can either have a stronger field or leave the field on for longer. So you know, if I play out a constant magnetization for 1 millisecond, maybe I get to here. If I go for 2 milliseconds, it just goes to there. Okay. Yeah. So anyways, you know, and you'll notice I'm using my hands a lot, and that's what MR physicists do. We're always sort of, you know, figuring out where the magnetization is going and making weird gestures with our hands. Okay. Because it is a very physical sort of phenomenon. So if you think about what is the magnetization doing with your fingers or your hands, that can also help you with your homeworks. So this is the final thing. So basically, the transverse magnetization, we said we can write it as a complex number. it's now going to satisfy this differential equation. All we've added is this T2 decay term. And the solution turns out to be as follows. We have an initial magnetization, M0. We have the precession, which we talked about before, which is just the minus omega naught going around. And now we've got this T2 decay term, which just means that instead of going around forever, it's just doing a death spiral. Okay? So that's what the magnetization looks like on the right-hand side. So we start off with magnetization. In this case, we're saying 1 is equal to M0, and then we just sort of traverse this trajectory. And as you can see, there's the precession, and there's also decay. So that's the picture you would like to have in mind for T2 decay. All right? And the longitudinal part just grows back. And so in this movie, what you're going to see is basically that same phenomenon occurring. So magnetization is decaying away, and then it's also the M sub z component slowly growing back. Okay, and you notice in this video, the MXY component usually dies away much faster than the M sub z recovers. All right, so I'll play that again just so you can see that. So MXY is basically done now, but M sub z is still recovering. Okay, and that's because T1 is always longer than T2, and oftentimes it's much greater. So for example, in brain, T1s are on the order of 1 second, okay, but T2s are on the order of 100 milliseconds. So there's like a 10-to-1 ratio between T1 and T2 in like a human brain at, say, a 3 Tesla magnetic field. Okay. And so this is another way of showing that. So basically, this is showing everything at once. So you're sort of seeing the MXY component decaying away, and at the same time the M sub z is coming back. Okay? But because the MXY decays much faster, it's basically everything's decaying away, and then this one's going back more slowly. Okay. So I think that's it for relaxation. Any questions on that? So once again, we'll revisit the fundamental mechanisms of this in a later lecture. Okay, so now we're going to really focus on MRI gradients, and we'll have a bunch of exercises for this to sort of help get the concepts in mind. But just to remind you, there are 3 gradients. There's an X gradient, a Y gradient, and a Z gradient. And each of those has a specific job. It is to create a linear gradient in that direction. And the gradients are always of the BZ field. Okay? And that's a picture of an actual gradient at the Siemens factory. So if there were no gradients, then the field would be, in an ideal case, would be uniform. BZ would equal B naught wherever you are. All right. When we apply a gradient, then now BZ XYZ is equal to this uniform main field, B naught, plus some delta BZ XYZ. Okay, so we're adding on an additional field. So let's assume we're adding on a X gradient. Okay, so this is going to be a gradient in the X direction. So now delta BZ of X is equal to GX times X, where GX is the gradient field. So what that's going to look like is this. As a function of X, if I'm right at the origin, then the spins precess at gamma B naught. So that's what's called, in MR terms, we call that the isocenter. Okay, so this will be at the isocenter. So in an MR system, everything is referenced to this isocenter of the magnet, where at that isocenter, there's no added field. Okay, so at 0, GX of times 0 is always 0, so there's no added field. And then as you go away from that, the fields either linearly increase or linearly decrease. All right. So what that means is these spins here, if I'm a spin out here, if I'm over here, I'm going to precess at gamma B naught plus gamma GXX. Okay? And if I'm going to spin out here, so I'm going to precess faster than a spin that's precessing at the isocenter. All right? And if I'm going to spin over here at minus x, I'm going to precess at gamma B naught minus gamma GXX. This should be the absolute value of x, right? Okay, showing the minus, it's in the minus thing, all right? Question?
How is gamma determined?
Gamma is a fundamental physical constant for every proton, so it's basically measured. Okay. Yeah. Okay. Okay, so let's do a problem together. We'll do this problem together. This is actually problem 12.1 from Prints and Links. And then we'll do some exercises. We'll have some other exercises. So here's the question. A non-uniform field B pointing in the z direction is applied to a sample of protons. The B field varies as, so we have B of z equals 1 plus 0.5 times z. Okay? And so the magnetization precesses around the z-axis. So we assume we've already tipped the magnetization, so they're all precessing around. Okay? And so at time t equals 0, all the magnetization vectors are in phase. Right? We've tipped them all. So the idea behind the magnetization is at time equals 0, we just tip the magnetization. So whether I'm here or here, I'm at the same phase. Right? Now, in the presence of a gradient, this one is going to precess faster than this one. So I want to ask the question, how long do I have to wait till they get back into the same place? It's like I have two runners. One's running faster than the other. At what point, at time equals 0, they're at the same place on the track. How much time do I have to wait till they get back to the same place on the track? All right, so that's the question. All right, so let's work through that. So the first thing is to realize that really this thing doesn't really matter, right? Because it's constant to both, right? That's the constant precession of both of them, because that's due to the uniform field. So if I'm talking about two spins relative to each other, that constant field doesn't really matter. Okay? So all I really need to worry about is this delta BZ term. Okay? Okay. So this delta B is equal to 0.5Z is equal to 0.5 times 1 Tesla, so it's 0.5 Tesla. Okay? Because we were given that, let's see, what were we given that? Yeah, well, we're given that Z, we're asked to look at Z at 1 centimeter. Okay? And the function is a function of centimeters. Okay? So we know that the difference between these two spins is half a Tesla, which is a huge magnetic field, right? That's a big magnetic field to have a difference in spins over half a centimeter. So there's really no gradient in the world that does that, but for this problem, we've set it up that way. Okay. So now what we want to do is we want to look at the difference in the frequencies of those two spins, right? So that's just taking the delta B. Okay, we remember delta omega is equal to gamma of delta B. Okay, in general, we always have omega equals gamma B, right? But when we talk about cycles and things like that, it's much easier to go into hertz. So what we want is delta F is equal to gamma over 2 pi delta omega equals gamma over 2 pi delta B. Or sorry, this is over 2 pi, right? Okay, so that's all we have. So what we can do is we can solve for that. So we know that the change in frequency between those two spins is 21.285 megahertz. Okay, so now what we ask is how long, if I have a difference in frequency of spins, how long does it take for them to get back together? And that's essentially one cycle of that oscillation, right? So then we can say that delta F times delta T is equal to 1 cycle. And so delta T must just be 1 over delta F. So it's relatively quick. It's, I guess that's 47 nanoseconds. It's a huge field, so it doesn't take very long for them to get back into phase. Okay, so that's problem 12.1. So then I added to that, this was from a previous homework from a previous year. What will the phases be at z equals 0.25, 0.5, and 0.7 centimeters, 0.75 centimeters at that time you calculated? So there's two ways to go about this. One is just to think about it and go, oh, it's obvious. And the other way is to just crunch the numbers. So we'll do both, all right? So let's think about it this way. I have these two spins. They're spaced by 1 centimeter apart, right? Okay. And I said if I wait delta t, then those two spins are in phase again, right? So if I'm in another spin here, which is only half the way, 0.5 centimeters. Oh, wait. Let's see. Yeah, 0.5 centimeters. So basically, if I wait delta t, these two spins are back in phase, right? If I wait that amount of time. So if I only go half the distance, which way will that spin be pointing? What should the angle be? What? Okay, so here are the possibilities, right? So this is theta equals 0, and this is theta equals 0 again, right? So now we're asking, for that spin in the middle, he experienced half the gradient, right? Because he's only half the way. So his delta B is only half as much as the one at 1 centimeter. So how far will he have traveled in that delta T? 90 degrees is one option. There's another option. Okay. Go ahead. Pi. Okay, so we have pi over 2 or pi. Okay. So who votes for pi? Okay, who votes for pi over 2? You want to change your answer? Okay, okay, pi. Right, so it is pi, right? Because he only goes half the way around the circle. Okay. What about the spin at 0.25 centimeters? What would his angle be? So that would be this spin here. Negative pi over 2, right? I mean, the answer is on the next page, right? So negative pi over 2, right? Because he's only going to go half, a quarter of the way. And then this one, so this guy is going to be pointing here, and then this one is going to be pointing up there, right? Because he's going to go 3/4 of the way through. Okay?
So the spin is always in clockwise?
Yes, so for all these problems, for the rest of this quarter, spin is always going clockwise. Yeah. Okay. Any questions on that? Okay. Yeah, sure. So we've got this gradient field, right? That looks like this, right, as a function of z. And so if I look at a spin at 1 centimeter away from the isocenter, we calculated that in that delta t time, that spin starts off at 0 and makes it all the way back to 0. Okay. So if I pick a spin that's halfway between the two, that's only going to make half the travel. So in that same delta t, so it's only going to get to pi, right? And if I pick a spin here, which is a quarter of the way, then it's only going to go a quarter of the way of that cycle. So that's minus pi over 2. Okay? So the other way you could do it is you could just do it by brute force. Okay? You could say the phi, my angle, right, is always going to equal, whoops. Let's see, my delta omega times the time that it took. Okay, so angle is always just equal to what's your delta omega. And then because it's a clockwise precession, it's going to be a minus, right? Just the same way we had, for example, that theta was equal to minus m naught of t. If I have a delta omega, it's just going to give me a minus delta omega of t. Okay, so this is, so in this case, basically we know that the delta, let's just do this one here. So this one, the delta omega, is just going to be, let's see, 1/4 of my 2 pi delta f that I calculated above, right? Because it's only 1/4 of the way there. So its magnetic field is 1/4 as strong as the one at 1 centimeter. And then I have my delta t. Okay. So this is basically, these terms here are my delta omega. This is my delta t, and then I have a minus sign here. So that's minus pi over 2. So, so it's a very simple example, but if you have any questions, think about it, and feel free to ask me in office hours or later. If you get this example, then it means you sort of understand what's going on. All right? Any questions before we move on? All right. Yes?
When we say clockwise, are we looking in the positive direction?
Well, all I mean is x, y, the magnetization always goes this way. So we've defined the xy coordinates, right? Yeah, so x, y, and z, right? Z would be pointing up. So, right, we have z. So it's always the right-hand rule, right? Z, x, and y, right? I think that's right. Or is it the left-hand rule? Whatever. X, y, and z, right? Yeah, whatever. X and y, it's going to go around like this. So that would be a left-hand rotation. But for the purpose of this class, basically just have that picture in mind. Theta is equal to minus omega naught t. If you just remember that, then theta is just always negative as a function of t. All right? Okay. Okay, so I'm going to do an in-class exercise. And remember when we talk about rotating frame of reference, we're always saying that we're not going to worry about this overall precession. We're just going to worry about the relative we're going to take out this sort of common frequency that's going around and just worry about the relative difference between things. All right? So there was a very famous scientist, Erwin Hahn, who had this saying that he invented the spin echo in 1950, and he said, there's nothing that nuclear spins will not do for you as long as you treat them as human beings. Right? So for this next exercise, we're going to sort of flip that on its head and do a little experiment to sort of get across what an MR experiment is doing. All right? So for this experiment, we actually need 5 human volunteers, so you all qualify. And I need you to come up to the front of the room. Okay? So I just need 5. It's totally painless. There's no harm involved. So. Okay, great. So we do need one more for this to work.
Don't all jump up at once.
Okay, so these are your 5 spins, okay? So what I'm going to ask, I'm going to give you some instructions. So what I want you to do is, first of all, get into a single file line facing that way. Single file. Give yourself some space between you because you're going to be rotating around your own axes. Okay. All right. So these are your 5 spins, okay? And the first thing we're going to imagine that there's a magnetic field pointing this way. So the magnetic field's pointing towards, you're in a large magnetic field that's pointing towards the ceiling, okay? So, and then at time equals 0, I'm going to excite you, right? And you're going to precess, okay? And the field is the same for everyone, all right? So when I say go, you're going to start precessing, all right? So that's the first part. Right, so you guys decide how you're going to precess. And then we'll see if you actually acted like spins would act. Okay? So ready, set, go. No, you can stand straight. Yeah. Just imagine your nose is the spin. Yeah. Okay, stop. Okay, so that was pretty good. So what could they have done a little better? Well, yeah, they could have spun fast. Well, it seems a very low field, right? So, so did they precess in the right direction? Yeah, they did. They all went clockwise. What could they have done slightly better? They did a very good job, but what could they have done? Like, yes.
I think you should.
No, let's. Imagine your nose is the spin, right? Yeah. No. You can face forward so you don't fall over. Okay. So were they totally in sync? No. So if you're in the same field, you want to be totally in sync. Okay. So let's start again. This is where the coordination part requires. Okay. Ready, set, go. Okay, good. All right. Yeah, it's much harder for the last person. Okay, so that was much better. Okay, so that's the first principle, that if you're in a uniform magnetic field, all the spins will precess at the same frequency, right? So that's the first thing you should get from this exercise. So go ahead and face that direction again. Now we're going to imagine we're in a rotating frame of reference, and when I say go, I want you to precess. Okay, ready, set, go. Okay, so what does the audience think about that? Was that the correct answer? So we're imagining now we're in a rotating frame of reference, right? So in a rotating frame of reference, what should the spins do? They shouldn't do anything, right? Because if they're all in that frame of reference, there's no rotation. Okay. So the person in the middle, what's your name? Nehan. Okay, so now we're going to actually apply a gradient field where the gradient is going to be stronger going that way and weaker over here. And Nehan is very special because she's in the isocenter. Okay, so unfortunately your job is going to be very boring because no matter what, you're just going to stand and keep facing that way. Because she's going to be in the isocenter, so in the rotating frame of reference, she doesn't move at all, right? Okay, The person at the very end, what's your name?
Up and
Up or down. Okay, so you are in the strongest field, okay? So you're going to rotate faster with respect to isocenter. So every time I say step, you're going to rotate clockwise by 180 degrees. That makes sense? Okay. And the next person, your name is? Rahul. So you're in a slightly stronger field than the isocenter, but not as strong as the person at the end. So you're going to rotate 90 degrees clockwise every step, okay? And your name? Ben is going to be in a weaker field, right? So he's going to rotate 90 degrees counterclockwise every step. And you are? Diban is in the weakest field, okay? And he's going to rotate minus 180 degrees clockwise at every step, okay? So we're going to sort of diagram this experiment as we go along. So yes?
Minus 180.
Sorry, 180, it doesn't really, yeah, 180 degrees counterclockwise. Yes, right. Yeah, so everyone understand their jobs? Okay, very good. So imagine this is at time equals 0. So we're going to document this. This is time equals 0, right? So imagine if the spins were like their noses, right? So their noses are all pointing in the same direction, right? So I'm drawing this up here. The spins, you can take a look at that too. Do you agree with that, how you guys look? Okay, all right. So, and let's say this is a function of x, okay? So that's the x and we're applying a gradient g sub x. So our field is gx, all right? Okay, so where are we in k-space at this point? So my contention is this is someplace in k-space. What does kx equal for this orientation of spins? 0, right? Because they're all pointing in the same direction. So there's no variation in this direction. So we're at kx equals 0. Okay. So now we're going to go to t of delta t. Okay. Step. All right. So here, this one is there. That one is here, right? This one is here. This one is here, right? And this is here. Everyone agree with that?
That one should be the other way? Oh, no, it's right. Okay.
It's correct. But good for checking. Okay. So what is the spatial period now? So assume this is delta x. What's the spatial period here? Right, so basically the spatial period is this. So how many delta x's is that? It's 4, right? All right, so this is 1, 2, 3, 4 delta x's before I have the spins in the same direction again, right? So now kx is equal to what? 1 over 4 delta x. Okay, everyone got that? Okay, so step. Okay, so now we have, so we're at 2 delta t now. So we have the spins going this way, this way, this way, this way, and this way. Right, so now what is my period in terms of delta x? 2 delta x, right? So my kx is equal to 1 over 2 delta x. Yes, question? Okay, so spatial frequency is all 1 over the period. Right, so that's all it is. Okay? So now we're at a higher spatial frequency, a smaller period. Okay, step. Okay, so now we're at 3 delta t. So the spins are going this way, this way, this way, this way, and this way, right? So what is my period here?
Again,
4 delta x, right? So what kx am I at here?
X.
Minus 1 over 4 delta x. So that's what a negative frequency means. So how does that differ from our other 1 over 4 delta x? Yeah, the orientation is different. So the experiment, the exercise you just did, the orientation of that helical helix is different, right? So here, notice these guys are pointing in the opposite directions of those guys.
So negative frequency is just like direction?
Yeah, it's just the direction of the helix, whether you're going this way or this way. Okay? All right, step. Okay, so now where are we at? Yeah, so for this experiment, we're back to 0. Okay? So great, you guys all did a great job. Thanks. Okay, good job. All right. Okay, so that's basically a way of just describing how we use gradients to impose different spatial patterns of the spins. All right. So on the next page, it's just drawing that a little more cleanly. Okay. So you can sort of see here, this was kx equals 0, right? There's no spatial variation in the orientation of those spins. The next one is kx equals 1 over 4 delta x. We're assuming that this is delta x. Right? Because the period is 4 delta x, right? The next one is kx equals 1 over 2 delta x. And then we said that this one is minus 1 over 4 delta x. Okay? I mean, we could have flipped the sign, so I'm not being too careful which gets the plus and which gets the minus. But if one is plus, the other has to be minus. Okay? Because this spin is pointing in the opposite direction of that, and this is pointing in the opposite direction of that spin. All right? And then at the end, for this example, we're at back to kx equals 0. Because we've sort of only sampled the spins with this delta x. All right? So this is the basic concept. If you get this concept, you sort of understand a little bit, you sort of understand the basics of why the gradients are so useful in MR, because if we apply a gradient and we allow time and we look at the evolution of the spins over time, the relative phase of those spins has different spatial patterns. Okay, and that's what, so the amazing thing is when we actually do an MRI experiment, when you go in the MRI scanner, first of all your spins get aligned, polarized, and then we excite your spins, and then we start opposing these weird spatial patterns on your spins. Okay? Yes, question?
Just to clarify, why isn't the first and the last case kx equals to 0 and not 1 over delta x?
Okay, so you mean why is this 0?
Yeah, and why not 1 over delta x? Because that's
Oh,
what we
okay.
calculated for the other case.
Right. Okay. So it's because we can only do the experiment with a bit of. I've imposed some sampling here, right? Because I can only have one human every delta x. In general, we'd imagine many spins, and there's no, basically, they're all the same. So if I imagine 1 million spins or 1 million people in this row, they'd all be pointing in the same direction. So however fine you go, it's always going to be pointing in the same direction. But that's a good question. Okay. And similarly, this is actually wrong because if I had all those spins, they would actually be pointing in different directions. But this sampling of delta x doesn't let you see that. So it's actually a sampling issue. All right? So this is actually should be at a higher frequency. This should actually be kx equals like minus 1/2 delta x, or it should be something. It should be larger. It should be kx equals something. I'd have to figure out what that means. But what you're seeing is the fact that we're only looking at spins every delta x. If we went finer, you would actually see the other spatial patterns. Okay. So we'll review that a little bit when we get to sampling. All right. The hard part about MR is like there's so many different concepts, so I have to like tell you a little bit at a time. And so, yeah. Okay, so now what we're going to do is we're going to do a little bit of background, and then about 4:45 after, we're going to give you guys an exercise to do together. Okay, so once again, if we look at the expression for the Fourier transform, we have our object, and we have this thing here. This is just a definition of the Fourier transform. And now what we want to do is spend some time relating this to what we just did with MR. Because if you understand the MR part, then it's going to help you understand the Fourier transform part better. All right. So notice this thing. It's e to the minus j 2 pi kxx. Right? So if it's just a math class, we just stop there and we do all the things possible. But now, since it's a medical imaging class, we want to give this a little more physical intuition. So first of all, we realize this just has the form of e to the j theta. Right? And so if we're therefore theta must equal minus 2 pi kxx. All right? So that's shown here. And in fact, and now you see why Fourier transforms are so useful. Even the sign is correct. We've got a theta of minus 2 pi kxx. All right. So let's assume that we're at the case where kx is equal to 1. Okay. And we're at x equals 0. And so we're just going to evaluate that argument. So what we just do is we just plug and chug. 2 pi kxx. So this is theta, right? So when x equals 0, theta must be 0. right? So that was the spin at the isocenter. It was always at theta equals 0, right? The theta at a quarter is would be experiencing a stronger field in our example. So that's going to be at 2 pi kxx. Let's see, should be a minus, right? Right. So then the theta is the minus of that. So minus 2 pi kxx equals minus pi over 2. Okay, and so that theta is equal to minus pi over 2. So just by plugging in for this kx, so kx equals 1 means that the period is 1, right? So period is just 1 over kx, so that equals 1 in this case. So we know in a full period the spin should return back to its orientation. So I've only gone a quarter of the way. It makes sense I've only gone a quarter of the way rotation, all right? And similarly, for x equals a half, I've gone half the way, so now theta equals pi. And if I go to 3 halves, this should be 3/4, sorry. Then I've gone 3/4 of the way, and so therefore theta equals pi over 2. Okay? So that's just sort of re-emphasizing that you want to think about this 2 pi kxx as telling you what angle you are at. All right, what angle is the magnetization at? So in this case, we're going to actually now play a different game. We're showing spins at different locations, minus 2 delta x, minus delta x 0, delta x, 2 delta x. And we're varying the kx from 0 to 1 over 8 delta x to 2 over 8 delta x, which equals 1 over 4 delta x. Okay, so let's look at that. So for the first row, that makes sense, right? All the spins are pointing in the same direction, and therefore we're at the center of k-space. Okay. If we look at the spin at isocenter, that's also correct because that doesn't experience any additional field, so it's always going to be pointing at theta equals 0. Okay. Now we look at the other spins, and we can do a sanity check. We look at this. Well, from here to here, it's like half a cycle, right? Because one's pointing up, the other's pointing down. So we know half a cycle has a period of 4 delta x, so a full cycle must be 8 delta x. So therefore, that makes sense. Kx does equal 1 over 8 delta x. Okay? And then in the last row, we see that the full period is here. It's the 4 delta x. Okay? And so that matches up with that. And so what you're seeing is that for each different kx, you can sort of just, it's basically telling you how long does it take before the spins align again. All right? So if it takes me this from here to here before the spin aligns again, then that's my period. The quicker that happens, the higher spatial frequency I'm going to be at. Yeah.
So in CG, we were looking at how many photons were hitting our detector as a way to understand, to gather the data to reconstruct an image.
Yep.
In this case, we're looking at the precession of hydrogen atoms or whatever we're visualizing over
Yep.
time as we change this gradient.
Yep.
How does the data acquisition for that gradient actually happen? Or how does that data acquisition for the precession of your different protons actually happen?
Yeah, so that's a good question. So imagine you're all spins in this room, right? And you're all giving off a magnetic field. The way I do, and I just measure what you're all giving me. And the idea is that if I rearrange your phases differently, then the sum of all those will be different. And so we'll talk about that.
Okay.
Yeah. Yeah. So the idea is we're always listening to all the spins at the same time. And so that's that integral sign. And so basically, in the Fourier transform, this integration is done by the RF coil. So basically, we impose these spatial variations on the spins, and then we listen to see what all those spins do. And then we go to another spatial configuration and listen to what they do then. And then that's how we step through k-space. So at every point in time, there's a different spatial orientation, and we're listening over time. Okay? So it's very different from CT, where it's sort of like, you're sort of, can imagine rastering through. It's basically, it takes time to encode, and you have to go through k-space. Okay? Okay, so just to review, the Fourier transform these are the expressions for the Fourier transform. And then so we have image, we have K-space. I'm going to go through these next few slides fairly quickly because it was covered in the supplementary session. So either you know Fourier transforms or you don't. And so if you don't, then the supplementary session can give you background. But we will, what I'll do instead of going through all of it very slowly, we'll revisit these concepts throughout the next few weeks. Okay. So the basic idea is what we can do is represent these complex exponentials as just plane waves, right? That's the easiest way to think about them, such that the period of the plane waves, if I just have a kx, then it's 1 over kx. If I just have a ky component, it's just 1 over ky. And for diagonals, the period is given by 1 over the square root of kx squared plus ky squared. All right? So that's what a cosine 2 pi kx plus 2 pi ky would look like, where the bars represent sort of the peaks of the cosine. All right? And so that's just sort of showing you mathematically how it happens. If you forget, you can always, one thing that is useful though that I will review here is if I give you an arbitrary point in k space, kx, ky, okay, if you draw a vector out to that, okay, then the orthogonal components to that will tell you the variation in space that that Fourier component refers to. And then the spacing of this in spatial domain, so in space, so is just going to be given by, is just going to look like this. Okay? Where that is going to be 1 over the magnitude of that k vector. Okay, the magnitude of this k vector is simply square root of kx squared plus ky squared. So this is just going to equal 1 over square root kx squared plus ky squared. So that just means that the further out I go in k space, right, the magnitude of that k vector gets bigger and bigger. So that's going to require 1 over k is going to get smaller and smaller. So the period is going to get smaller, right? And then the orientation of those lines just depends on which direction the k vector is pointing. So if the k vector is pointing along the ky, then the spatial patterns are going to be these stripes, right? If it's pointing along kx, the spatial patterns are these stripes. So anytime you see a problem, then it's always going to be just sort of the orthogonal to where it would be in k space, right? And the center of k space is really important, and we'll talk about that more. But basically, as we talked about last time, it is basically, if I think about the center of k space, kx equals 0, then this just becomes 1. And so it's just the area under the curve. If I have a two-dimensional image, it's the area of the image. And so it's basically the overall, the mean intensity or brightness of your image. Okay, so that turns out to be a useful quantity to know about. And so we typically, when we refer to things like signal-noise ratio or optimizing our thing, we're always thinking about, how do we maximize its value at the center of k space? So just to review, this is showing different points in k space. So if I'm here in k space, it corresponds to stripes like that. As I go farther out, those stripes become finer, more closely spaced together. If I go along the ky axis, so this is the kx axis, so the ky axis, now I have these stripes like that. And then if I go farther out, those stripes are more closely spaced. And then if I go diagonally, then I have diagonal stripes. All right? So that's the picture you should have in mind. And notice if I draw a line to here, and I think about the perpendicular to that line, that's essentially tells me the orientation. So this is a movie just reminding you what the parts of k space are responsible for. So this is showing, this is the k space here, and this is my image. So if I just use the center part of k space, that just gives me the overall brightness of the image, and here a little bit of the low resolution details of my image. So it's a very blurry version of my image. And what we're going to do in this movie is we're going to incorporate more and more of k space, and you're going to see the image details fill in. All right, so here we go. Okay, so play that one more time. So the center parts of k space give you sort of the overall structure of your object, and then the outer parts of the k-space starts filling in the details. So it'd almost be like, you might have a building, the center part of the k-space tells you have a building and about how big it is, and then the finer parts of the k-space fill in sort of what that building looks like. All right?
Does that center point relate in the k-space relate to like just the DC gain or whatever of the system itself, and then all the other frequencies will give you that?
Yeah, so the center part of k-space is, basically, if I have an object, it's just imagine I averaged all the spins in that object together. Yeah. So it's basically the mean value of my object. Yeah. So here are some examples where here, if I zero out this part of k-space, then I'm going to lose the information about edges going like that, right? So if you notice here, this edge here, whoops, sorry. This edge here is now much blurrier than the original edge there. Okay? So these edges left, right are much more blurry. Whereas this edge here, sort of these edges here are still fairly sharp because I've kept that information. All right? And then imagine adding on some energy in k-space. Okay, so this is basically, and these are artifacts that we sometimes see in MR, where you'll just see these are called zebra artifacts or corduroy artifacts. Every once in a while, there'll be some extraneous energy that gets into your system, and where it occurs, depending on where it occurs in time, will lead to where the image occurs. So, for example, if that spurious component appears here in k-space, it's going to give rise to these stripes. Okay, so if I think about drawing the vector from the center of k-space out to that component, then it's going to have stripes like that, right? So that's why the stripes are up and down, like that. Similarly, if the spurious component happens here, then that's here in k-space, so the stripes are in that orientation, and that's why the stripes occur like that.
What is an example of the spike happening?
It can be very simple. So one thing happens, so you might have like someone just didn't tighten up two wires very well. And so even just micro movements of wires tapping each other can cause enough electrical energy to cause a spike. Yeah, go ahead.
So in the top example, the spike that was below the k-space
Yeah.
actually caused the horizontal streaks.
That's right.
And if the spike was actually further down south,
Yes.
You would have more streaks, right?
They would be finer spaced, higher frequency.
Higher frequency. Would
Yeah.
the width of these streaks be slimmer though?
If each one was just a little spike on its own, then the size of the streaks would not. What you're seeing here is the spacing between the streaks would be, would get finer, and then just depending on your display, that becomes a resolution how you display it. Then it might appear fatter or thinner. Yeah, but in reality, they're waves. Yeah.
So if it's at a diagonal,
Yeah.
depending on what angle of the diagonal it's at, it makes sense that you'll shift the angle of your artifact.
Yeah.
If you're along one of the axes or along the center, does that make any difference? So sorry, if it's 20 units spaced above your center versus 20 units below the center, does that make a difference to the image reconstruction?
From the point of view, these are magnitude images, so from a magnitude point of view, it wouldn't matter because you either have a cosine of 2 pi, plus pi 2 pi kx versus a cosine of minus 2 pi kx. And so now you would be able to detect it if you were more phase sensitive, but most images are typically, we just take the magnitude. In that case, it wouldn't really matter. So you wouldn't be able to tell unless you did a little more work. Okay. And you might not be able to tell because once you get the images you get are already processed for you. So unless you have access to the raw data, you wouldn't really be able to tell.
So just to, I get the thumb rule, I guess. But
Yeah.
The explanation is that you take the inverse of that, or Fourier transform of that point in that and put it here, then you get like a sinusoidal. Sorry, yeah.
Like a complex exponential.
Okay.
Yeah.
Yeah, so e power x plus y.
Yeah.
Okay.
Okay. Okay, so then, So we've talked about mostly stripes. So it's useful to think about stripes as the first thing about Fourier transforms. But since we're talking about MR and what we really have in the Fourier transform is complex exponentials, it's actually we want to start transitioning from a view of actually thinking about what the spins look like. Okay, and so the argument is these are sort of in this case you can sort of see that. Let's see, do they have the spins? So sort of see there's a stripe. So this is sort of the overall striping pattern of that. Okay, so you can start looking at, we're actually not putting stripes into the body. We're actually just orienting the spins at different phases. But the spatial pattern of that orientation is what can gives sort of something that's analogous to stripes. Okay. So for example, this would be in 2D the center of k-space. So this is kx equals 0, ky equals 0. So there's no variation in x and there's no variation in y in the orientation. All right. This is now kx equals 0, but ky does not equal 0. So here, if you look along the x direction, on any given row, there's no variation of the orientation, right? But if I pick any column, there's a lot of variation. Okay? So therefore, that's kx equals 0, but ky is some other value. Okay? So let's take a look at some examples here. So this would be kx equals 0, ky equals 0. And for this case, there is no difference, there's no spatial dependence on the orientation of spins. Okay. Here I've got kx equals 0.25, ky equals 0.5. So let's see if that makes sense. So what's the period in the x direction? So this is the x direction. So how long does it take me to get the spin back to the same orientation? 4, right? So the period here is 4. So that makes sense. That's equal to 1 over 4. Okay. What about in the y direction? What's the period? 2, right? So that's 1/2. So that checks out. And here we've got kx equals minus 0.25, ky equals 0.5. So how is this different from, how are these guys different? Do you notice the difference between those two? Yeah, the direction, right? So this one went this way, whereas this one went that way. So the orientation of the spins, one went this way, the other one went that way. But the period is still, the magnitude of the period is still 0.25, or 4, and so the period, the spatial frequency is still 0.25. And here we have kx equals 0.25, ky equals 0. So now you notice this period is still 4, but there's no variation in the y direction, so we're at ky equals 0. All right? So that's how we start thinking about k-space. Question?
So again, in CT, what we were plotting L versus theta,
Yeah.
and our data information for how many, for attenuation was intensity or how many photons were detected.
Yep.
So in this case, kx, ky, what are we looking at with regards to intensity?
So here's the way to think about, the cool thing about MR is you can make it look like CT. Okay. So if I wanted to make an MR system look like CT, so in CT, remember, every angle you're acquiring a projection. Okay. If you take the Fourier transform of that projection, it gives you a line in k-space. Okay. So what CT does is basically it acquires lines in k-space like that. Okay. So this is kx, ky. Okay. So it just fills in k-space with radial lines. Each of those lines in k-space, okay, if we broke it into different, so if I had a line in k-space like that, and I broke it into different parts of that, each of those points is one point in the MR acquisition, because each of those points corresponds to a different spatial pattern, right? So CT acquires the whole line at the same time because there's a whole projection, and then it gets all those points. MR is collecting those points bit by bit by bit.
And what are we encoding into each of those dots as when you're trying to go back to, so you're drawing your line, you're putting together all these points,
Mm-hmm.
kx, ky, that feature is all of your photons aligned in the same direction, or the spin is in the same direction, your phase is the same. How does that get encoded into your ky space? Is it counting how many photons are in a certain direction, or yeah?
You mean in MR?
Yes, in
Okay.
sorry.
In MR, it's essentially you think it's probably easier to think about what's the sum of the magnetization.
Okay, that's the.
Yeah, so basically at every point in time you're looking at the sum of the magnetization. And so depending on the spatial orientation of the spins and its interaction with the object, which we'll get to in a few minutes, that magnetization will vary from k-space point to k-space point. And that's what we're measuring. And then once we have that data, we just put it in MATLAB and take the inverse transform and you get your object. Okay. Any other questions? Okay. So yeah, getting to that point. So the way the Fourier transform works is we're going to take our object here. And we can imagine multiplying it by, this is representing our e to the minus j 2 pi kxx term, right? And then for 2D, obviously, we have kyy, right? And then this dv would be our dx dy, all right? And this would be a double integral. Okay. So basically, we take our object, we sort of impose this pattern on, and then we integrate that thing, all right? And that gives us one point in k-space, so we store that point in k-space. We go to another point in k-space, it's the same object, we impose some spatial pattern onto it, so that's a multiplication, and then we integrate it, and that gives us another point in k-space. Okay? So that's sort of the simple picture of it. But in MR, it's actually, instead of thinking about these stripes, we actually want to start thinking about these spins here. Okay? So we take so mathematically, it's as if we took our object and we multiplied it by some phasor pattern. So this is our phasor pattern. And then we integrate it and we get that. Okay?
So,
yes.
So the direction of the phasor pattern, I guess, is on the whole determined by like the upward and downward floating ones, or like the ones that are in phase? Because like at each line there are some spins that are in phase and some that aren't, right?
Yeah, so the way to think about it is if you're given the phasor pattern, so like a problem that you could be given is I'll give you like a picture of spins in some orientation, and the question would be where are you in kx and ky? So for the way to think about it is kx, if I give you kx and ky, right, that's just two numbers, that whether the image is 100 by 100 or 4 by 4 or 5 by 5, that determines the spatial pattern of the spins in that image. And you fill in the details, right? So that's basically saying kx is how much variation I have in the x direction, and ky is how much variation I have in the y direction. So every point in k-space tells you something about the whole image. Okay, it's not just one part of the image. So that's one thing to really make sure you understand. It's sort of hard, it's sort of confusing, but each point in k-space is the whole image. It's the whole pattern. Okay? And it's only by seeing that whole pattern that you can tell where you are in k-space. We'll do an example, maybe not today, but maybe next time, where if I take away some of those patterns, some of those spins, you won't actually be able to tell where you are in k-space. You actually have to look at the
zeroing thing?
Yes, exactly. So if I zeroed out some of those, if I just got rid of some of those spins, you might not be able to tell where you are in k-space.
Is it because of something like, since you don't have the data,
exactly.
all the points that correspond to that spin?
Exactly, yeah, yeah.
So which means that, for example, this set of spins,
yeah,
like at some particular k-space, it might represent what the image looks like at like 10 different points or 20.
Well, this is just, if I sample my object with this sampling, that is sort of what the spins would look like in that object. Now, if I could take a microscope and look at even finer detail, I would see between those spins other variations of spins. Okay. So yeah, it takes a while to get your head around this, but the idea is for today, realize that we apply the gradient. Each time we apply the gradient, we impose a spatial pattern in the spin orientations. Every kx, ky point corresponds to a different spatial orientation of those spins. Okay? So let's just finish off. I think we have 5 more minutes, so let's just finish off with an example, and then I'll set you up for the exercise for next time. So this is sort of thinking about the MR experiment. So imagine this is like a bar of, I don't know, this is like a granola bar or something, right? It's got some spins in it, right? I put it in the magnet, and and I've imposed this spatial pattern on the spins, right? And it's let's say it's a uniform, it's like a power bar, it's like all the same gook, right? And you don't really know what's in it, but there's stuff in it, right? So we imagine all the spins are uniform, and there's stuff everywhere, okay? So now I'm at this point in space, k-space, and so you can sort of see that the spatial pattern here is like that, right? These are the peaks where things repeat, right? Let's see. So there's some spatial orientation of the spins there, right? So that's where they're repeating with some period. But my bar is sort of a uniform object, right? So that uniform object is not really a good match for something that has stripes. So now the MR signal is the sum of all those spins. Okay, I'm at some point in kx, ky, and I sum up all those spins, and I get the value of the Fourier transform. So because all those spins are sort of in different directions, when I add them up, I get a relatively small net magnetization. Okay, so that's the basic idea. Now let's say I take my bar and I say, well, I want to impose some spatial information on that bar. So I'm going to cut out chunks of that bar. I'm just going to make diagonal cuts in that bar and take out some of the spins. Okay? So if I do that, my bar looks like this now. Okay? And so these are all the parts I cut out, right? Which is the same as multiplying by 0. Okay, so the multiplication MR is just whether the spin is there or not, or how much of the spin is there. It's not like we have a multiplier in your body. It's more just the multiplication essentially. If there's a lot of spins there, then they all get that phase. And if there's no spins there, that's like 0 times that phase term. Okay? So now if we think about it, I've cut out the bar, all the parts of the bars that were pointing like spins pointing in one direction. So I'm left with all the spins pointing in the same direction. So if I think about summing up all these spins, now all of a sudden I get a really big magnetization vector. Okay, and what that means is this Fourier component, which has variation like that, is a pretty good match for my object. Right? My object had these diagonal variations, and my Fourier pattern also had those orientations. Okay, so that's the basic idea. So we've got a number of things going on at the same time. We have our object, right? We have the spatial pattern we would lay on the object, and then we have the integration, which is we're summing up all the spins. All those things mean that when we do that, this is the information for this object at one point in Fourier space. Okay, and we have to do that over and over again until we fill up Fourier space. Right? Okay, so the integration of the signal is just done by the RF coil. Okay, so basically it's seeing the magnetization from all the spins. Okay, so that's nice. We don't have to have some integrator. It's just this analog integrator that does it for us. Okay. Now, we did talk about, there can be array coils where we have many, many RF coils, in which case it becomes more complicated because then we have to think about how do we sum up all that information. So maybe if we have time towards the end of the course, we'll talk about that. All right. Okay, so we'll end with the recipe for the Fourier transform. So this is the equation for the Fourier transform, right? So obviously if you're doing it in a math class, that's all you need to know, right? You just apply this equation to lots and lots of different functions. But since we're doing MR, we want to actually think about what's the physical picture of doing this. So here's the physical picture. For each k-space location, we use the gradients to create some spatially varying phasor pattern. Okay, so we've seen examples of that already. So we know we can use gradients to create this phasor pattern. Okay. We then multiply the object gxy by the phasor pattern to obtain the product gxy times that phasor pattern. But when we actually do it, there's actually no multiplication. It's just the fact that if there's more or less spin there, that's the multiplication, right? If I have an area in space that has 0 spins, then gx is equal to 0 there. And so, there's no spins to look at, right? If I have a lot of spins there, then there's more spins that can contribute, and they all have that phase associated with them, all right? And then I integrate the product over all of space, and so that's done with my RF coil. And so each of that just is one point in k-space. Okay, so I do all that. So basically I do all that, and then I go to the next point. Okay, and I pose a different spatial pattern and integrate it, let the coil integrate it, and then store that information. And then I go to the next point in K-space. All right, so that's what we'll be talking about in the next lecture, is how we actually go about doing that. Was there a question there?
Is that, so essentially each of those points means that every time that you sample, you're taking about a second or so to induce your spin, take your data, encode it, and then go on and do so again?
So when MR first, well actually what we do is, in some scan, you could do that, but that's really slow, right? Your subject will be like dead by that time. So typically we either acquire one line at a time, like remember we had 100 milliseconds or 50 milliseconds to acquire data. So we can acquire the data very quickly, or we can actually be really greedy and try to collect all the data in that 100 milliseconds. So for things like functional MRI, where we want to actually measure the brain like every second, we actually try to acquire the whole brain every second. Okay? So we'll talk about that when we get to K-space trajectories. Okay, so no class on Monday, so we'll see you on Wednesday, and then there will be office hours on Tuesday, right?
2 to 3, but there'll be an announcement if you look up.
Okay, and there'll be a short homework posted either today or tomorrow. Okay.
Next week.